Okay, let me introduce dot products. We're back to vectors. In order to understand dot products, this thing originates from physics. It was first developed because physicists needed it, but then later it has some good mathematical properties, so we mathematicians use that a lot too. But in order to understand dot products, you first have to understand something called a projection. What's a projection? Well, in physics 1, you may have solved problems like a block resting on a slanted surface on an incline, and the force of gravity is pulling it down, and in order to solve this, probably the question is more like how fast does this come down, what's the acceleration? These are the questions that are being asked, right? And often what's needed in solving these type of problems is that you have to write this vector as components, where one component is in the x direction along the incline, and this one, which is perpendicular to the horizontal direction. Right? So you need this calculation which projects one length to another direction. So what you're required to do is that if you have a vector and you have some kind of an angle, and to ask what's the component of this vector along this direction is to actually figure out this magnitude. This is being asked, right? You have to do this a lot, right? Okay. So how do you do it?
Sine and cosine.
Use sine and cosine. That's good. Which one should we use? Sine or cosine?
Cosine.
Should be cosine because it's in between. So to be more specific, this is a right triangle where this side is adjacent and this is the hypotenuse, and you can say that cosine of theta being adjacent over hypotenuse, it should be written as this question mark over the norm of that vector. And therefore, this part is now, you can call this part as the norm of V times cosine theta. Now, such a calculation is called the projection. You're saying that you're projecting V along this vector, which we call this as U. If we call this vector as U, projecting V along U means exactly this calculation. You can write that as a formula. So here's the first formula that we're going to use for dot products. Projection of V onto U is defined as follows. You take the norm of V and multiply by the cosine theta, where theta is the angle between U and V. That's called projection. So you are in fact using this many times in physics without really knowing that it has a name. It's called projection. Now the next thing I want to say is some formulas make use of the projection and in a way that it's part of the formula. So let me show you another formula that you use in physics. It's called work is force times distance, and you multiply by cosine theta. Have you seen this? What is that? Why do you need this cosine theta? If you have this block, if your force is not along the horizontal plane, and you're just doing this, then you know that the portion that's, if you divide this into components, this component only is lifting this, but it's not really doing the work. Right? The one that's really doing the work is the one that's projected to this horizontal horizontal line. So you have to do F times cosine theta, and then once you get this projection, you multiply that by the distance. That's what this formula is saying, right? Work is force times distance times cosine theta. If you look at this, here's what's happening. You can think of the force as a vector, force, and you can think of this d as a vector because it's a displacement. Displacement is a vector. Distance is a scalar, but displacement is a vector. So you can talk about the circumstances like this. I have the force, and I have the displacement. And I'm saying in this case, the work is obtained by taking the norm of the force, the magnitude of the force, magnitude of the distance, times the angle theta, cosine of the angle theta. Okay. You can rewrite it like this. And physicists realize that this type of calculation happens a lot, not just here. There's also, what's another one? Suddenly I can't think of any other case. But it does appear in many other contexts in physics. Okay? So they made a new notation, which goes like this. They just said the work should be force dotted with the distance, where this dot product is understood in the following way. If you have a vector u dotted with vector v, it's defined to be this thing. So the norm of the first thing, the norm of the second thing, and then times cosine of the angle. Yes?
So all three of those equations are the same?
This is same as that. Yeah, all three. Yeah, all of these are the same. Okay. All three are same. And it's nice because this dot product thing satisfies some good mathematical properties. See, we mathematicians want nice properties because if something doesn't have good properties, then we can't use it for calculating things. If it has nice properties, then it makes life easier. So we looked at it and said, well, the angle, cosine of an angle doesn't change if you replace theta by negative theta. So whether you measure from u to v as positive 60 degrees or v to u as negative 60 degrees, or is it okay? From here to there as negative 60 degrees, positive 60 degrees or negative 60 degrees, it gives you the same value. Cosine function has this property. And that tells us that u dot v is same as v dot u. So that's a commutative property. it's good to have something like that. If we don't, then every time you switch things around, you have to get nervous. Am I making some error here? But because we have this, we have some peace of mind. Another really important property that we like is called the distributive property. A distributive property requires two things: multiplication and addition. Right? And here's what you can think about. If you have one vector u, and let's say here's another vector v, and let's say this is a vector w. Now, if you project the first thing, project the second thing, and then multiply. So let's see. Let me first write down the distributive property. That's easier to explain that. Okay, so what I'm trying to say is that w dotted with u plus v satisfy the distributive property. What does that mean? This is equal to what? I can distribute, right? So w dot u is w dot v. That's what I want. Now let's think about this thing. What is this? This is, first you project u onto w and multiply by w. So it's basically this white line times this much. This much. And this one, w dot v, means this much times this length. Whereas here, you're saying u plus v, you're adding these two vectors, so you're adding these two vectors, coming up with the third one, and then projecting this down here and multiplying. Now let's since multiplying w's magnitude is a little confusing and it's being multiplied everywhere, let's just divide both sides by the length of the w so that this all means this projection. Okay, just think about the projection. Is it true that this plus that is same as this much? Right? In other words, if you project u onto one vector, v onto another vector, and add them, is it same as first adding the two vectors and then taking that projection? Looks confusing. Looks convincing, right? No?
Yeah.
Looks. I mean, it pretty much says it. I mean, okay. Or if you don't agree, then you can at least show that this length is same as that by showing that these two triangles are congruent. So you can actually geometrically prove that this length is same as that length. Therefore, this plus that is same as this plus that. Okay. So I didn't actually write out the proof, but it is true. Okay. So you have this distributed property. Now those two properties are really good properties. Let me show you why. First, let's call I vector and j vector as vectors of length 1, one in the x direction and one in the y direction. Now I'm using this hat instead of arrow. That means it's a unit vector. So whenever you see a hat, that's supposed to mean a unit vector. Okay. So in your physics textbooks, whenever you see this hat, you should interpret it so. Okay. Now, if I have a vector that's 2I plus j. See, I'm doubling the I and I'm adding j, so I get this vector, right? And let's say I have another vector which is I plus 2j. Let's try to take the dot product of the two. How do you do that? Well, if it weren't for the distributed property, we would be just sucking our thumbs that we don't know what to do. Yeah. Just staring at it, not knowing what to do. But now we have the distributed property. What does that mean?
Distributed.
You can distribute, meaning that you can basically FOIL it, just like how you handle regular multiplication. So I can do this, which is 2I dot I. And I refuse to say I squared because if you just say I squared, that could mean something else. So you want to say I dot I, okay? And you have I dot j plus 2j dot 2i plus 2j dot j. And these are easy to compute. How do you calculate this? What's the definition? Norm of the first, norm of the second, cosine of the angle. What's the angle between I and I? 0. It's the same vector, so if you have the same vector, I and I, their angle is 0, right? So 0. What about this? Norm of I, norm of j, angle. What's the angle between I and j? J is going up, I is going here, cosine 90 degrees. All right, do you know what cosine 0 is? Cosine 90 is? Oh, so this is 0. In fact, the very formula that we're writing down immediately says that if two vectors are 90 degrees, they're 0. Any orthogonal vectors are 0. And then, how about this one? Twice of j dotted twice of j, I. What would that give us?
4ij.
4ij, but what's I dot j? That's my question. 0, 0, 0, because they're perpendicular. Any orthogonal vectors will give you 0, so this will be 0. And then twice of j cosine of? Huh? 0. It's the same vector. They're both, this is j, that's j, same vector. If you're, any vector has 0 degrees away from itself. Okay. Any vector is 0 degrees away from itself. Okay. So this is, what's this thing? What's the norm of I? 1. It's a unit vector. I said it's a unit vector. Okay. So this is 2 times 1 times 1, so that's 2. Those are zeros. That's 2 times 1 times 1 times 1. So that's 2. So we get 4. So that enables us to compute these vectors on the plane. Now I'm going to turn this thing into a formula so that you can do it easily next time. But that's basically my introduction to dot products.